Good evening, everyone. Can you see the screen? Yeah, okay. So far only 26 people have joined. I don't know why. Let me. Okay, we'll start. Let the others join. Okay. So today we go into. We'll look at gasification systems. Okay. So in the previous lecture, we saw. We studied about the principles of combustion and the properties of biomass. Okay, can someone summarize the previous lecture? Anyone, just a short summary would do, whatever we had. Or should I
Sir,
point fingers?
we solved problems relating to the stoichiometric oxygen needed to
Yeah,
needed
that
to
is
yes, oxidize
one
the.
part of it. No, I mean, you just say, just list out what all we did in the previous lecture.
Yes, we calculated the heat of fusion, then the adiabatic flame temperature,
Yes.
and
So that
how
one
to
is
estimate
pending.
the flame temperature problem.
Yes, that problem is pending. I'll do it right now. Okay.
Okay, sir. Yes, sir.
So we saw the principles of combustion. So there was also this biomass properties. Okay, we missed out on that. So the proximate and ultimate analysis of biomass, where how you can measure the moisture content, ash content, volatile content, and fixed carbon. And then we saw an example of the Cassarina wood, the approximate and ultimate analysis of Cassarina wood. And then we had a few questions on the stoichiometric oxygen requirement, stoichiometric air requirement, all of these things. Okay. So now so in today's lecture, we'll just have a recap of the combustion fundamentals. Then I'll go back to the question that we had left in the previous lecture, and we'll solve that today. And then we'll go into the challenges in biomass combustion. What is equivalence ratio? What is gasification? And then we'll see a few gasification reactors like fixed bed reactor, fluidized bed reactor, and drain flow reactor. And then there is a downdraft fixed bed downdraft reactor at IISc. So we'll have a short intro to that one. And then the gasification system. Okay. So the reactor, the technology that the reactor uses, and then we come to the gasification system. And then we'll see the air gasification versus oxygen gasification. I've just mentioned this in passing over the past few lectures when we saw the biomass conversion technologies and the pathways and everything. Then some definitions related to gasification, and then we go on to the discussion. So for combustion, you need three major factors. One is the fuel or the combustible substance. Then you have the oxidizer, which is air or oxygen basically. But since air contains oxygen, you could also have air as the oxidizer. And then you should have sufficient temperature for the combustion to start and sustain. So at room temperature, you cannot have combustion because there should be an ignition temperature. There's an ignition temperature for each type of fuel, and you can start burning it only after you reach that ignition temperature. Okay. So what is heating value? So heating value is the amount of heat or amount of energy released when you burn any substance, any fuel. Okay. So it can be determined through a device called Baum calorimeter. So there is an experiment for that. I didn't go into the details. You can just look it up. You can find it on YouTube also. Okay, and heating value can be expressed as higher heating value or lower heating value. So what is the difference between the two? Anyone?
Sir, the moisture content, whatever water is moisture, H2O is released, it is either in the gaseous form or liquid form. So in a higher heating value, we consider
Mm-hmm.
the water in liquid form.
Okay, and lower heating
Then,
value?
then even the energy released out of the water gaseous vapors converting in coming back to the liquid state is also
Mm-hmm.
considered. And in lower heating value, the
Mm-hmm.
that that part is not considered.
Yeah, you're right, but it's not moisture exactly, because moisture would mean the moisture contained within the biomass, right? That's
Okay,
not the
yeah. So
true. That's not
whatever
the case. Yeah. So even if you have dry biomass, absolutely bone dry biomass, you will still have higher heating value and lower heating value. Okay.
yes,
And
yes,
it is the H2O released upon combustion, because biomass contains carbon, hydrogen, and oxygen. So the carbon and hydrogen will form CO2 and H2O, either with the oxygen within the biomass or from the oxidizer. Okay.
yes, sir.
And so that H2O, which is released upon combustion, should can either be in liquid form or gaseous form. In reality, it is only in gaseous form, but we can consider that it is in liquid form. So it kind of it loses heat to come back to liquid form, right? So that heat is also released, and that also we consider to be available to us for, I mean, in our assessment. In reality, that's not the case. Okay, so lower heating value is a much accurate, measure of the actual heating value of the material, or yeah, of the fuel. Okay. Next, we spoke about the stoichiometric ratio. So, what is the stoichiometric ratio?
Sir, stoichiometric ratio is the amount of oxygen required to burn any fuel to
Yeah,
completely burn it.
yeah. So it is the amount of oxygen required to completely combust 1 kg of any fuel. Okay. And then, so yeah, it is different for different fuels based on the stoichiometry, that is based on the amount of carbon or hydrogen that each of these fuels have. Okay. So for example, if you have just carbon, C plus O2 gives CO2. So 1 mole of carbon will require 1 mole of oxygen, which means 1 mole of carbon is how much? 12 kg. Okay. Or 1 kilomole is 12 kg. 1 kilomole of oxygen, sorry, uh, yeah, so 12 kg. 1 kilomole of oxygen is 32 kg. So 1 kg of carbon will require 32 by 12 kg. So it is around what? 2.66 something, right? We saw it last time, 32 by 12. Yeah, 2.66 kgs. So 1 kg of carbon requires 2.66 kgs of oxygen for complete combustion. Okay. Now, what is adiabatic flame temperature?
The temperature it can the temperature we can achieve after burning a substance inside a closed system.
Yeah, isolated system, not closed, because
I,
closed system
okay.
can have energy interactions. There is no
Energy
energy
exchange.
interaction
Yes.
in this case. There is no
Yes.
heat loss to the surroundings. So if there is no transfer of heat, the heat, I mean the heat transferred across the system is zero, which makes the system adiabatic. Okay. So
Yes.
if that is the case, all the heat that is generated by the combustion of this of this fuel is released just to the species that are formed during combustion, like CO2 and H2O. Okay, the only place the energy can go is increase the temperature of these species. So that temperature in the condition of no heat transfer across the system boundary is called the adiabatic flame temperature. Okay, so we'll come back to the problem from last week. So basically, what happened is that so we had considered only oxygen as the oxidizer. CH4 plus 2O2 gives CO2 plus 2H2 is what we had considered. Okay, so that is okay if pure oxygen is the oxidizer, when in reality there we will use air, for the combustion. Air will contain nitrogen. So we'll see how to calculate in both cases, right? So the first step is to write down the equation, the chemical reaction. Okay. So if you have only oxygen as the oxidizer, you have this reaction which you have already written down. Or if you consider air, I think there is a mistake here. There should be a two. Oh, sorry. It's right. Okay, so if there is air as the oxidizer, then what happens? You have an extra 7.52 N2. Why? See, because this is the formula for air, the average formula for air, if you remember from a couple of lectures ago. So there is 79% nitrogen and 21% oxygen in air. Okay, so we represent that as this 1O2 and 3.76 N2. So the total number of moles over here is 4.76. One mole of oxygen and 3.76 moles of nitrogen. Okay, so 1 and 3.76. So remember this. Then you have this extra term 7.52 N2. So essentially the N2 is not reacting because this is we are considering ideal case, because in real case what happens, because of the high temperature there is some NOx formation. The nitrogen and oxygen react to form nitrous oxides, nitrogen oxides. So NOx, okay, it could be NO, NO2, NO3 and so on. Okay, but here we consider that the nitrogen is inert, it doesn't react, it just comes out. So whatever goes in comes out here. So the enthalpy of reaction, the approximate enthalpy we calculated yesterday, which was right. So if we consider 50 megajoule per kg as the LHV of methane, then you convert that into kilojoule per kilomole, you will get 800,000 kilojoule per kilomole. But if you want to do it accurately, more accurately, so this is based on an assumption. Assumption is that, but it is realistic. It's like 50 megajoule per kg. That's a very realistic assumption. But if you want to calculate more accurately, you can calculate the enthalpy of the reaction through using the enthalpy of products and the enthalpy of the reactants. So how do you do that? It's just the enthalpy of the products minus the reactants. So if you so from this table you know the enthalpies, okay, and you have the equation here. Okay, so you have to calculate one time of CO2 enthalpy plus 2 times of H2O enthalpy, and this is enthalpy of formation. So you have both here. Okay, CO2 and H2O. So 1 time of this, 2 times of this. Add both, and then minus the reactants. So here you have 1 time of CH4 and 2 times of O2. So let's have a look here. So 1 time of CH4 is this, O2 is 0. Okay, so you just have to calculate it that way, and then you will get this number 802,405. So this is approximate. This is the actual number that you get. So there are different estimates based on the enthalpies of formation and all that. So I'm doing it based on this table which I've shown over here. Okay, so there are some studies that show like around 890,000 kilojoule per kilomole and so on. So that's also perfectly fine. It depends on the enthalpies that you have at hand. Okay, so using this, I've calculated 802,000. Here we have 800,000. So we are very close to the actual number. Okay. Now, why is this negative sign appearing? So negative sign is appearing because it is an exothermic process. Burning is exothermic. It releases a large amount of energy, large amount of heat. Okay, so any exothermic process has a negative enthalpy of reaction. This is true everywhere. This is by convention. So this is true everywhere. Okay, and the how exothermic is it? Is it mildly exothermic, or is it too exothermic? That depends on the number itself. So you can see this is a huge number, right? So even if you convert this into kilojoule per mole or something, it's 802. So that's quite a big number. So there are some reactions that have like minus 41, minus 50, minus 100, and so on. So those are mildly exothermic reactions. Okay. Okay. So moving on. So this entire enthalpy, and whatever enthalpy is here, right, that goes into rising the temperature of the products, which is CO2 and H2O, or in this case, CO2, H2O, and N2. Okay. So here you have delta HR, that is equal to Cp times delta T. Okay. And Cp you can calculate using this over here. Right? You have two times of H2O, 1 time of water, and 7.52 times of nitrogen. Okay. So if you're using only oxygen, then this is what you will get. So this number times delta T, or you add a 7.52 times 33.71 times delta T. So equate both of these to this number that you got. So you don't have to, carry the sign forward. Okay. Now, now calculate the delta T. So you just have to divide this by this number, right? So the delta T, if you are using pure oxygen, is 5574 Kelvin as per these numbers, which is very high, right? It's about 5200 something degrees Celsius, which is quite high. Okay. But if you use air, it is about 2018 Kelvin. So that's about 1800 something, 1700 something degrees Celsius. Okay. Now, the delta T is nothing but the adiabatic temperature minus the initial temperature, because adiabatic temperature is the final temperature that you are supposed to calculate. You know the initial temperature, which is given over here, 298 Kelvin. Okay. So now you just have to add this number to the initial temperature, and you get the temperature, the adiabatic flame temperature for both oxygen, the case of oxygen, and for air. Okay, this is more realistic because because you'll be using air only for calculation for the combustion, right? You won't be using oxygen, practically speaking. Okay, so are there any doubts in this as to how to calculate and?
Sir, in
Yeah.
practical situations, we don't have an isolated system, right? So there will be a
No,
loss
you
of.
don't. You don't. This is just what is the maximum temperature that you can reach upon combustion. That's what we are calculating here.
Okay.
In
Okay.
ideal case.
Yes,
So
sir.
what is the maximum we can reach? So no matter what happens, you cannot go above this, or you can't go above this. So it's just calculating the maximum temperature that can be attained. Okay.
Yes, sir.
Okay. So moving forward, so coming to biomass combustion now. So we spoke about combustion in the previous lecture. Now let's see what are the challenges in biomass combustion. Okay. Like I said, the NOx formation it is possible. See, because you have the flame temperature, adiabatic flame temperature of above 1500 degrees Celsius. So the nitrogen in the air will react with the oxygen in the air to form NOx. Okay. Yeah. Anything? Okay. So the nitrogen and oxygen will react to form NOx. Okay. And NOx is a pollutant, so it's not. It causes a lot of respiratory issues and everything. So it's a pollutant. Then there's also particulate matter due to the ash content in the biomass. Okay. So according to the life cycle assessment, around 74% of all environmental impacts arising from wood combustion is attributed solely to NOx and particulate matter. So it's the same continuation of the same point. So NOx and PM10. So only 2% is attributable to CO2, and that also comes because of the transportation of the wood and the other processes that are happening, not due to the wood combustion itself. Okay. Why is that so? See, 2% is attributable to the CO2 arising or emitted during wood combustion or in the process, right? So I'm saying that that is due to the processes, the auxiliary processes like transportation, and not exactly the wood combustion itself. Why? Yeah, that is true. Vehicles release pollutants, but I'm asking why is it not due to the wood combustion itself? I mean, wood combustion also releases carbon dioxide, right?
Sir, the carbon dioxide released during wood combustion is
Hmm.
whatever carbon stored in the wood itself.
Yeah.
That's why.
So why is that not? I mean, it's the same for coal. Whatever carbon is stored in the coal is released during combustion. So why is that an issue and wood combustion not an issue?
Because coal, whatever carbon was stored in
Yes,
coal, is from a long time ago.
exactly.
And
See, it's carbon neutral.
yes, yes.
Carbon neutral, right? So that's the reason why CO2 is not such a big issue when it comes to the environmental assessment of biomass systems. More weightage is given to the NOx emission and particulate matter. So we are not contributing anything to the global warming as such, but then we are still contributing to air pollution. Okay, so that also needs to be toned down. So yeah, so the next point is, so you have a lot of inorganic elements because of the ash in the ash, right? So if the temperature is more than 1000 degrees Celsius, the inorganic elements in the ash will fuse together to form kind of like a boulder kind of thing that's very hard. So it's called a clinker. Okay. So what do clinkers do? I mean they just block the reactors, right? They form clinkers and they block the reactors, and then it's you need to dismantle the whole thing and remove the clinker, and then only you can uh, resume your work basically. Okay, so that's not desirable. And this is especially true for high ash content biomass. It won't happen for wood because for wood it's less than 2% ash. But rice husk has about 20% ash. Rice straw has about 13-14%, something like that. So we need to ensure that either the temperature does not exceed this limit, 1000 degrees Celsius, 900,000, maybe less than that, uh, or we need to ensure that the ash is periodically removed. Okay, I'll tell you how when I talk about the IISc gasifier. Okay. So there are different types of pollutants that are produced as a result of combustion. So you have unburned pollutants such as tar, soot, hydrocarbons, carbon monoxide, ammonia, nitrous oxide, and so on. And there are pollutants arising from the complete combustion, such as NOx and carbon dioxide. Although carbon dioxide is not such a big issue, NOx is a very big issue. Then you have the ash and particulate matter. Okay. So particulate matter is again released to the atmosphere. So coming to the equivalence ratio. So there is stoichiometric air requirement or stoichiometric oxygen requirement. Okay. So it is the mass of oxygen or mass of air required to completely combust 1 kg of biomass or 1 kg of any fuel. Okay. So let's take that as X amount. So if let's say I have a biomass that requires X amount of oxygen for complete combustion, ideally. Okay. Now what I do is I can either give more than X or less than X or exactly X, or I can give zero also. You get the point. So I require X amount of oxygen to completely combust 1 kg of biomass. I say I'll give 2x times. I'll give 2x amount of oxygen. So what is that process? If I require x, I give the system 2x. What is the process called? Are you sure?
Combustion.
Yeah, exactly. So if I require x and I'm giving more oxygen than required, what is that process? It's combustion, right? What is gasification? Gasification is if I give less than x. And if I say that I require x amount of oxygen, but I will give only 0.3 times x, then that is gasification. And what happens if I give no oxygen? If x equals zero, if I give 0 times x?
Pyrolysis, sir.
Yes, exactly. Okay. So how do you measure all this? So how do you know whether a process is pyrolysis, gasification, or combustion? You do that through something called equivalence ratio. What is equivalence ratio? So it is exactly in the denominator, you have the stoichiometric requirement, okay, which is your x. On the top, you have what you are providing, okay. Let's assume that my biomass requires 6 kgs of air for complete combustion. I am giving 2 kgs of air. What is the equivalence ratio? Why is this taking too much time? I'm saying that my stoichiometric requirement is 1 by 3. You can mention that in decimals also, 0.33. Okay. So 0.33 is my equivalence ratio. So what is that process in this case?
Gasification.
Yes, gasification. So I require how much? 6 kgs of oxygen to completely combust 1 kg of biomass. But for the same 1 kg of biomass, I'm giving only 2 kgs of oxygen. So which means it is deficient in oxygen. So I need 6 kgs, I'm giving only 2 kgs. So I'm only giving 33% of the total requirement for combustion, which means I'm in the gasification territory. Okay. If I say, okay, I'll give 12 kgs of oxygen instead of 6 kgs, what is that process?
Combustion, sir.
Combustion. Okay. So let's take one more example here. So if 34.28 kg of oxygen is supplied for a process involving the combustion of 2 kg of diesel. So I've given the formula for diesel here. What is the equivalence ratio? Can you calculate? First, you have to calculate the stoichiometric requirement. Then you have to calculate the equivalence ratio. How do you do it? I mean, let's go step by step.
So first we get the balanced equation.
Yes. So you do that.
C10H plus O2 gives CO2 plus H2O. So we need for 1 kg of C10H20, we'll need 15 kgs of O2.
We need what?
15 moles of O2 for
So
one.
I mean, can you just write down the balanced equation on chat?
Yes.
Yeah. Okay. So C10H20 plus 15O2 gives 10 CO2 plus 10 H2O. Right. Okay. So you have this. Now you tell me the stoichiometric requirement of diesel. Yeah, but we're not talking in moles here, right? We're talking in kilograms. How do you calculate the stoichiometric requirement in kilograms?
Sir, for 1 kg of diesel, we require 10.9 kg of CO oxygen.
How?
15 into 32.
15 into 32 is?
15 into 32. Just a minute. For 44 kg of diesel, we'll require 15 into 32.
So Nishmit, this 480 kg is for 1 mole
480.
of diesel. You have to convert
Yes.
even that 1 mole into
480
kg.
divided by 44 we have to do.
Why 44?
480. Because 44 is the 44 kg is C10H20.
Are you sure that's 44?
This means 12 into 10 plus 20. 44. Yes, sir.
12 into 10?
12. Oh, shit. I did 12 into 2. 24. 12 tens are
Yeah,
120.
140. Yeah,
140. Yes, yes, yes.
140. Okay. Now you tell me
480
how
divided
many
by
kgs are
140.
required?
480 divided by 140. 3.43.
3.43 kgs of oxygen are
Oxygen
required to
is required
completely
to
combust
complete 1
1
kg of
kg of diesel.
diesel. Yes.
Okay. Now,
Yes.
3.42. Okay. Yeah. So now I've given you this question. Now can you tell me the equivalence ratio?
Yes. 3.428 divided by 1 whole divided by
So in the denominator, you have the stoichiometric. Numerator, you have the actual.
actual.
Okay.
Okay.
So
it is
it could
30.
be the other way also, but here we are following this convention. So it is only based on convention. But if you
This
are
one
following anything, you have to follow the same convention throughout. Okay. So here,
Yes.
there should be no confusion. Here we are following this kind of convention. So where stoichiometric is always in the denominator and the actual what we are providing is in the numerator.
Yes. So the equivalence ratio is 5, sir.
Yeah, how, I mean, you explain it.
Yeah. So as you mentioned here, yeah, the actual air given is 34.828 kg divided by 2 kg of diesel, and whole divided by 3.428 by 1.
Yes, yes, true. So that's it. So did everyone get this? Like how to calculate the equivalence ratio? Do you have any doubts? Anyone? Any doubts? Please ask. So tomorrow we'll be doing some calculations on using air also. So because until now we have only used oxygen. So calculations with oxygen are very easy because you have only one element there basically, right? So which is oxygen. We have only one gas. So in air you have O2 plus 3.76 N2. So you have to calculate the whole thing. Okay, so that becomes slightly more complicated. So tomorrow we'll do that, not right now. Okay, but if anyone has any doubts with this, how to calculate the equivalence ratio, please ask because this is very important. Anyone? So stoichiometric you just calculated, no? What did you calculate? So 34.28 by 2. So here you have the air or oxygen here in this case, 34.28. The fuel here is 2 kg. So air to fuel stoichiometric, you just calculated. How much is that? You just calculated from it's 480 for 1 mole, not for 1 kg. You have to convert everything into kg. Okay, 480 kgs of oxygen are required for 1 mole of diesel. Okay, remember that. You have to convert everything into kgs. So have we calculated it? Have we calculated the stoichiometric requirement? What do you mean? Can you just speak up instead of the chat if you can? Because I mean, I'm not sure I can understand them. Yeah.
Okay. For I'm a bit confused in the stoichiometric part.
Okay. So what is stoichiometric ratio?
The oxygen that's required to completely burn.
Yeah. The oxygen that is required to completely combust. That is basically how many kgs of oxygen are required to completely combust 1 kg of biomass or any fuel. Okay.
Yeah.
So that is the definition that we have given. Now I have given you this equation, this formula for diesel, C10H20. You have written the balanced equation for combustion of diesel. Have you? You written on chat, right? So you can refer to that. So what is the equation here? The reaction here. So C10H20 plus 15O2 gives 10 CO2 plus 10 H2O. Correct?
Yes, sir.
From this equation, what can you deduce about the stoichiometric ratio? Let's go first. We'll go for the molar one. So how many
moles of oxygen is required for 1 mole of diesel?
Yeah. So 15 moles of oxygen divided by 1 mole of diesel. You get it, right?
Yeah.
Now we have to convert both into kgs.
Okay.
Okay.
Oh, okay. I got it right now.
Got it?
Yeah.
So what's the stoichiometric requirement?
For 15 moles of oxygen for 1 mole, and then we have that's 15 times 32.
Yeah.
That's equal to 140 of C10H20.
Huh?
For
For
1 kg of diesel.
I didn't get it. Can you repeat that?
That's 15 times 32 oxygen.
So 15 times this 32 is okay. You have converted the number of moles of oxygen into kgs. That's fine.
Yeah.
So that 15 times 32 is 480 kgs required for how much diesel?
140.
For 140 kgs of diesel.
Yeah.
Right?
Yeah.
Yeah, 140 kgs of diesel. Why 140? Because that is the,
That's
according to this formula, that is the molar mass of diesel.
Yeah.
Calculating from this, right?
Yeah.
Okay. So now, so for 140 kgs, you need 480 kgs of oxygen.
Yes.
So how much do you require for 1 kg of diesel?
140 by 480 by 34.28 by 2 for the.
So why are you? I mean, I'm just asking about the stoichiometric. Oh yeah, you can still do that also. I mean, you can substitute it directly here if you want. But let's calculate the stoichiometric requirement first.
140 by 480.
Are you sure? Just write it down. Do the cross multiplication. No. So 480 kgs of oxygen are required for 140 kgs of diesel. How much do you require for 1 kg of diesel?
140 by
Huh?
yeah, so we can directly put it there, right?
You can, but I just want an answer from you. I mean, this stoichiometric
140 by 480. That's what
you're again you write it down, do the cross multiplication. So diesel on one side, oxygen on the other side. Go back to your 6th standard. That's okay. That's going back to the basics. Okay.
Yeah.
So even I do it this way. I mean, after coming
so
into
that's-
PhD, I still do it this way actually, because that's very effective.
Yeah.
Yeah. Yeah. So, okay, let me tell you this. So you need 480 kgs of oxygen.
Yeah.
For 140 kgs of diesel, right?
140. Okay. Yeah.
So now you need to convert that 140 into 1 kg of diesel. How do you do that?
480 by 140.
That's it.
Yeah. Okay. I wrote something else. I'm sorry.
Okay. No issue. I mean, you got it right. You had the fraction wrong. That's it.
Yeah.
So what is that? What is that answer? I mean, the stoichiometric requirement.
480 by 140. That's 3 point something. 3.42.
3.428.
Yeah.
Right. Now
Yeah.
you substitute on top. You substitute the actual, which is. So what is the numerator on top?
28 by 2.
Yeah, divided by
3.42. That's 5.
Yeah, that's it. You got it?
Yeah.
Okay, awesome. So now let's go into gasification. So why is equivalence ratio important for gasification? Because that kind of tells you which zone you are in. Are you going, I mean, what process you are following? Like, are you going for gasification, combustion, or pyrolysis? Or are you going for excess oxygen, I mean, for gasification? So over here, let's look at what is gasification, then we'll come to this picture. Okay, so gasification is the process by which a gaseous fuel is generated from solid carbonaceous fuel. Like it could be coal, biomass, or municipal solid waste. Okay, so that gaseous fuel can be syngas or producer gas. So the difference between the two I'll cover a little later. I've already told you this, I think, in the first or second lecture. Okay, so gasification is the sub-stoichiometric because you have a stoichiometric air requirement for combustion. So you're going below the stoichiometric air requirement. So it's called sub-stoichiometric combustion process. Okay. And it is a combination of oxidative pyrolysis and char reduction reactions. This also I will explain. So what is oxidative pyrolysis? So you have pyrolysis that is taking place within the reactor. During gasification, you still have one portion where pyrolysis takes place. The volatiles are removed. The char that is produced and the volatile gases that are released are further oxidized because of the supply of oxygen within the reactor. Okay, they are not completely oxidized. They're not completely burnt because the air is in limited quantity. Okay, they're still like there is char is basically carbon, right? So carbon becomes carbon monoxide instead of carbon dioxide, and the hydrogen from the volatile gases will become. I mean that will stay as it is, or it may get oxidized to H2O. Okay, stuff like this will happen. So that is oxidative pyrolysis. And char reduction. So char reduction happens because of the presence of H2O from the moisture or from the volatile gases, or you could give an extra supply of steam. So in either case, what happens is the char reacts with the H2O to form carbon monoxide and hydrogen. Okay, so this is called water gas reaction. Okay, and the carbon monoxide that is formed further reacts with the H2O if there is sufficient quantity of H2O present, either through steam or through the moisture itself. Then the CO reacts with the H2O to form CO2 and further more H2. So this is called water gas shift reaction. So there are two of these reactions that are taking place. So the char gets reduced to carbon. So yeah, there's also one more reaction. It's called Baudouin reaction, where the carbon dioxide within the reactor reacts with the char to produce carbon monoxide. So all of these reactions are taking place. So that's why it is called oxidative pyrolysis on one hand and char reduction. Okay, and that is what produces the syngas and producer gas. Okay, and there are four zones basically. One is drying zone, then pyrolysis, then oxidation and reduction. I'll come to this in detail in a couple of slides. Okay, and there are different types of reactors. There are fixed bed, fluidized bed, and entrained bed reactors. So coming to this diagram over here. So this on the x-axis, you can see the stoichiometric requirement. Okay, the stoichiometric requirement for combustion of coal. So this one is moisture and ash free coal feed. Okay, so stoichiometric requirement, or this is in the x-axis, you can find how much air we are giving related to the stoichiometric requirement. So this 2.5 over here, right? This is the stoichiometric requirement. Okay, so what is to the left of this and what is to the right, and at this line exactly? Can someone tell me? If I was not clear, so this 2.5 is the stoichiometric oxygen requirement for the complete combustion of coal. Okay, and this x-axis denotes the amount of oxygen that we are giving with respect to the coal, right? So that is the actual oxygen given. Yeah, now tell me. Yeah.
The line is a separation between combustion and gasification.
Yes. What is to the right and what is to the left?
On the right, it is complete combustion, and on the left, we have gasification or even pyrolysis.
Yes. True.
Does pyrolysis come under this only, sir?
Yeah, it does. So I'll tell you how exactly. So you look at this one, very low supply of oxygen or close to zero. So you can see from here, 0.1 to let's say 0.7, you see that there is a lot of carbon produced, solid carbon here. Why is that happening? Because there is pyrolysis. Do you get the point? Because of pyrolysis, solid carbon is produced. And you also have, of course, hydrogen from the volatiles, carbon monoxide from the volatiles. So look at this zone here, 0.1 to 0.7, right? Okay. Now further
Yes.
from here, right? From here until here or something, 0.7 to 1.9, something like that. That is gasification zone. Okay. So you have limited supply of oxygen here. So you have a lot of hydrogen that is produced, lot of carbon monoxide that is produced. But as and when, as you are increasing the oxygen, you see that the carbon monoxide is getting converted into carbon dioxide. The H2 is getting converted into H2O. So as you increase the oxygen supply to the reactor, the transition is slowly taking place from a combustion from a gasification to combustion. Okay. And as you reach this 2.5, what happens? You have completely CO2 and H2O. You see this? So it's fully CO2 and H2O. There is no CO, there is no H2, there's no carbon. It's only CO2 and H2O. Now, if you go further to the right, that is, you give excess supply of oxygen, combustion takes place, of course, but then this, can you see this? This O2 is appearing here. Can someone tell me why?
Because if we give oxygen more than the requirement, there is
Mhm.
some oxygen left which is not used.
Exactly. It does not react because there is more oxygen and there is no fuel to consume. Okay. So whatever oxygen goes in just comes out like this. Okay. So you have like the pyrolysis zone over here where you have solid carbon formation because of the pyrolysis, and you have hydrogen and carbon monoxide because of and of course CH4, H2S, all of these are in traces because of the volatile gases. Now in the gasification zone, as you increase the oxygen, you are moving towards complete combustion because the hydrogen itself reduces, the H2O increases, and the CO is getting converted into CO2 because of the excess supply of oxygen. The slowly as you're increasing, and as you reach 2.5, which is the stoichiometric oxygen requirement, you have completely only CO2 and H2O. And then as you go further, that is, you give more supply of oxygen, then you have CO2 and H2O, of course, but then you have a little bit of O2 that is coming out in the product as well because uh, there is no place for that O2 to go. It cannot react with anything because there is no fuel left. Okay, it just comes out with the product. Okay. Now,
So
the
whatever,
types, yeah.
so whatever here it's given is kind of like an ideal situation, right? And
Yeah, kind of, because see here, it is never complete combustion at
yeah,
2.5. You can never
yes,
see completely CO2 and H2O. You can always see a little bit of CO, little bit of H2O. Everything is like it's a mixture of everything. Although it's in traces, you can still find it. Okay, and the
yes,
reason is because not all the oxygen reacts with the entire fuel. Okay, so there's some unburnt fuel also. Okay, so this is an ideal case. Okay, so in reality, if you want complete combustion, you should always be to the right of this line, because that kind of ensures. So you're just giving something extra to ensure that everything gets consumed. That's how it is. Okay.
Yes.
Yeah. So even in that case, you won't get CO2 and H2O completely. You still have some traces of CO, H2O, all of these, right?
Yes.
So coming to the types of reactors, so you have fixed bed, fluidized bed, and entrained bed reactors. So what is fixed bed reactor? So in this case, you can see, so there are different types of configuration of each reactor. Okay, so that depends on um, the movement of the fuel. So here, this is coal. Okay, the coal is moving from up here, right? So moving from up to down. Okay, and the steam, oxygen, or whatever oxidizer you have is moving from down to up. So this is called counter current because it's moving opposite to each other. Okay. So what happens is there is a drying zone, there is a pyrolysis zone, oxidation happens over here. Okay, and and the whole thing is like they are moving counter current, and the gas is taken out from the top. Okay, and the ash is taken out from the bottom. Did you get this? Wait 1 second. Yeah. So there are different zones. Drying zone, which will be on the top when the moisture in the biomass is kind of, or in this case in coal, is kind of released. Okay, and that goes along with the gas. Okay, and that also kind of cools down the gas itself because the gas is at very high temperature because the oxidation takes place here, which is very highly exothermic. So the gas is at very high temperature. The gas loses a little bit of its temperature in this zone over here, the drying zone, because I mean drying zone, and that heat from the gas is sufficient to dry the or remove the moisture from the coal or biomass. Okay. Then comes the pyrolysis zone where there is less supply of air, so there is char formation and volatile gases. Okay. Then comes the oxidation zone where there is sufficient supply of oxygen. Okay, and the char is getting oxidized over here. Okay, and then comes the ash. I mean, the ash is collected from the bottom. Okay. So fluidized bed, there are two types of fluidized bed. One is bubbling fluidized and the other is circulating fluidized bed. So the basic, so what is fluidized bed? So you have a heat transfer material like a sand or something like that, which is usually rotating within the reactor. Okay. So it is tangential. There is a tangential entry so there it's like a cyclone. So you can see this cyclone, right? So cyclone, it's like rotating within the reactor, and the biomass or the fuel, right? The fuel that enters from here is also caught in this whirlpool, basically, and it is pulverized. It is in the form of a fine powder. Okay, so that is how it is like completely circulating within this reactor. Okay, and because the reactor is at a very high temperature, the heat transfer material like the sand or whatever it is transfers the heat to this particle, the fuel particles, and it is completely turbulent. There is a lot of turbulence within the reactor, so that kind of helps with the heat transfer. Okay, and the conversion takes place within the reactor. Okay. The difference between bubbling and circulating is that there is one loop over here. So there is a cyclone. This also has a cyclone, but then the cyclone is to remove the impurities from the gas. So the gas is taken out from here. Okay. To remove the impurities from the gas, like the particulate matter, you have a cyclone. The particulate the particles are heavy and then they are collected at the bottom. The gas is light, right? So it just goes to the top. Okay, and then it's just taken out. So here there is a recirculation. So along with the so the cyclone effect, so the particles they just are recirculated to the reactor again, so that if there is any particle that is unconverted, okay, instead of ash, I mean, other than ash, if there is some fuel particle that is unconverted, it comes back here and then it goes through the same loop again. And the gas is taken out from the top. Okay. Right. So this is what happens in a fluidized bed reactor. The entrained flow reactor is very similar to fluidized bed, but there is no fluidization as such. So the so in this case, there is the fuel and the oxygen is moving side by side. Okay. Here, both the fuel and the oxygen is introduced from the top. Okay, from the top. So the fuel is again pulverized in this case, but the oxygen kind of entraps the entire fuel into it, and then it converts the fuel into gas. Okay. The only difference between this and fluidized bed reactor is, I mean, in both cases, the biomass has to be pulverized, or the fuel has to be pulverized. Okay. The entrained flow reactors, they operate at very high temperatures and pressure. Okay. And the gasification reactions occur at very high rates. Okay. And because of this, because of the high temperature, what happens is if there is any tar formation, so the higher hydrocarbons and all these kind of unwanted oils that are forming within the reactor, right, which may clog the engines or whatever equipment you're using in the downstream, those have to be cracked within the reactor. So because of the high temperature, these tar particles are cracked within the reactor. Okay. And the ash, the temperature inside is so high that the ash first fuses into clinker. So I told you about clinker formations. They are fused into clinker, but then the temperature is even higher, that it actually melts. The ash kind of melts, and it's collected in the form of a slag down here. So there are some advantages and disadvantages with each type of reactor. Okay. So the fixed bed reactor normally has high tar yields if it is an updraft kind of reactor. So what is updraft? So this one is updraft because the gas flows from down to up. So this is updraft. If the gas flows from up to down, then that's called downdraft reactor. Okay. So of course, the one major drawback with fixed type is the scale limitations. You cannot scale it up. So you need small scale reactors, okay, for both updraft and downdraft types. Okay, but in downdraft type, it produces low tar because okay, I'll explain this in the next slide. Okay, and updraft can handle high moisture. Same with downdraft also, in fact. Now, if you look at the fluidized bed, then it's suitable for large scale applications. Even entrained flow reactors are suitable for large scale applications. And in entrained flow, there is very low tar. Okay. Whereas in fluidized bed, there is medium tar yield, which is still okay, if you ask me. Okay. But you need a separate reactor where you have to crack the tar, maybe increase the temperature or something like that. Okay. And normally you can produce very high heating value gas in fluidized bed and entrained bed. Whereas in fixed bed, you cannot do that. The heating value of the gas is very low. So this one is the open top downdraft reactor. It's a fixed bed reactor, downdraft type, because the gas is moving from top to bottom. Okay. So the reactor itself has like 4 zones. It's similar to the reactor that I explained earlier. So in the top, the biomass is fed from the top. Okay. And if you're using air as the oxidizer, then what happens is the air is also, it's open top, the lid is open. So the air is also coming from the top. Okay. So on the top, you have drying zone. So it's about 25 to 250 degrees Celsius. So the moisture is released, and the moisture in the form of vapor, it just travels along with the biomass and the air. Okay. Then comes the pyrolysis zone. So pyrolysis zone is about 250 to 700 degrees Celsius, where char is formed, biochar is formed, and then you have the various tars as well as volatiles. They're all traveling down. Now comes the oxidation. So here you have excess supply of oxygen that goes in. Okay, so you're basically whatever supply of oxygen is there, you're dividing it among the top and the nozzles. Okay, so maybe 65% from the top and 35% from the nozzle, something like that. Okay, and so you have the oxidation zone here because of the presence of oxygen in this vicinity. So the char gets converted into CO and CO2. Then the hydrogen in the volatiles get converted into H2O and so on. Okay, and so I was talking about the tar formation, right? So in the pyrolysis zone, tar is formed. But then in the oxidation zone, because it is slowly moving down, there is a lot of residence time, high residence time, even though the temperature is very less. So the tar is kind of cracked over here. So it gets oxidized to simpler substances. Okay. So there is very less tar formation in this case. Okay. And in the reduction zone, I told you about those about those reactions that are taking place. Like you have the water gas reaction where steam, in case you have steam, you have steam is reacting with char, or steam is reacting with carbon monoxide to form CO2 and more hydrogen. And then you have Baudouin reaction where the char is reacting with the carbon dioxide present within the reactor itself to form carbon monoxide. And then the syngas or producer gas is taken from here. So can someone tell me, like normally gases travel from down to up, right? If they are lighter than air. And this is definitely lighter than air because it has a lot of hydrogen, a lot of carbon monoxide and so on. Okay. So why in this case is the gas traveling from up to down, or how? Any idea?
Because whatever gas is formed, it is formed in the oxidation zone only after the pyrolysis.
Yeah, but even then it has to travel upwards, right? So if it is formed in the oxidation zone, it still has to travel upwards. And another thing, let me tell you, there are gases formed in the pyrolysis zone also. The volatiles. Volatiles are released and they are coming down. They're not moving up. Why?
Okay.
It's not a question of why actually, rather how. Because naturally it can't happen that way. It can never happen that way.
Is it because of the temperature difference?
No. I told you, naturally it can't happen. I'm asking you how it can be possible, how it can be made possible. So this is something that we have done. So I want you to guess how this is possible.
Oh, so there is a blower is used.
Yeah, I can see here, right?
Yeah, that's what. Yeah.
Yeah, that's it.
Yes, sir.
So basically, it's a device that keeps the entire reactor under suction. So this is
Like an exhaust
completely, yeah, sub-atmospheric pressure. It's less than atmospheric pressure here. And then the blower is somewhere here, and then the blower kind of, it's sucking the gas basically, and then,
Yes.
right. So that's the reason the gas moves from top to bottom in this case. Okay. And now I was telling you about removing the ash, right? So in this case, we have a screw conveyor at the bottom. Okay, there is a conveyor at the bottom where if we operate it, whatever unburnt particles, solid particles are there, they just fall to the bottom and then they are taken out. So we have ash content. Let's say we have a very high ash content biomass, like let's say rice husk, 20% ash. Okay, so we need to optimize the operation of this conveyor in such a way that it removes 20% of the feed. So if I'm feeding 10 kg per hour, I need to remove 2 kg per hour at the bottom. So I can optimize this conveyor usage uh, based on the feed, biomass feed that I have, based on the ash content of the biomass. Okay. But along with that, I'll also have some unburnt char, okay, which can be used later. Okay, the ash, of course, cannot be used, but the char can be. Char can be used for various different purposes, like maybe water treatment, or you can just return it to the soil, or whatever it is. Okay. So this is a system, the entire system. So you have, is this clear? Is this clear, or do you need me to increase the size or something?
Yes, sir, it is clear.
Clear, right? Okay. So this is the system, right? So you have the biomass lift from, so we just send the biomass over here, and there's a conveyor, a hopper, which travels to the bin, and then it drops the biomass. So this is hydraulically operated, pneumatically operated. And then, so this is the reactor that I just explained. So you have the screw conveyor over here collecting the char and the ash. It goes to a cyclone. The syngas, or the producer gas, goes to a cyclone to clean it further of all the particulate matter. And the particulate matter is collected in a bin over here. And the syngas travels further. So this setup that you see is a set of scrubbers. So what are these scrubbers? So you have atomized water on top. Okay, so it sprays water basically on the gas. So what happens? A few things happen. One is, if there are any more particles, any solid particles left over in the gas, they get entrapped in the water, and then they travel down because they become heavy, and then they are collected in this tank. Okay. And the second thing that happens is, because the water is at room temperature, the gas is kind of cooled down. So gas is at around 400 something while exiting. So the gas is kind of cooled down to room temperature. So what happens if there are any tar? So most of the tar is like cracked within the reactor. But then if there is any tar left over, then what happens is that that gets condensed. And because it is heavier than the gas, it travels along with the water, and it's also collected and in this tank. Okay. So we do that 3 times. So 2 of these are like normal water scrubbers. The third one is the chilled water scrubber, where we have a chiller, and we cool down the water to about 10 degrees Celsius, I think. And the gas, so if there are any more tars left in the gas, they also get condensed, and then they are removed from the gas. And the clean gas comes out at about 15 degrees Celsius, something like that. Okay. Then you have a powder coated filter. This is again kind of cleaning for the gas. And then after that, it can go to any utility. And the water over here is supplied, it is cleaned first. And so there is a water treatment plant, and then it goes to a cooling tower to lose the heat. Okay. So this is the entire gasification system. Any doubts on this?
No, sir.
Okay. Now, wait a second. Yeah. So now we come to the air versus oxygen steam gasification. So in air gasification, air is used as the oxidizer, whereas in oxygen steam gasification, you use oxygen and steam. Okay. So you have oxygen. Oxygen is the main oxidizer, but steam, superheated steam, is added to enhance the water gas reaction. And this is done to enrich the syngas. I mean, if you want more hydrogen content in your gas, then this is done, because it is H2O, right? And the steam reacts with the carbon within the reactor to form more hydrogen. So you use more steam to produce more hydrogen. Okay. Air gasification has lower investment and operating costs, but oxy-steam has high investment and operating costs. Can someone tell me why?
Because we have to get oxygen separately. We have to uh, get
That is
only
one.
oxygen from air. That's why that process is costly.
Yeah, that is one. What about the other? I mean, any other reason you can think of?
That is also an energy intensive process, right?
Which one? Of course, that is energy intensive, but assume that you are purchasing oxygen, okay, from outside. So that is that comes under your investment cost. So it is not operating. Okay, no, it is operating, of course, but what other reason can you think of, like why it has high operating and investment costs?
You should see, you should kind of isolate it so that it does not get contaminated with other things.
Isolated as in?
Like it shouldn't be mixed with other gases because you need only pure oxygen.
Yeah, I mean, you get pure oxygen anyway, right? If you can buy a cylinder, it's not mixed with other gases. I mean, it's the same reason that was given already. I mean, the oxygen part is covered. There's one more thing that is there in this case.
Sir, here not only oxygen is the investment, we also need a steam, something to
Exactly.
convert the
Exactly.
water to steam and mix
So
it with
even if
oxygen.
you're not producing oxygen within your plant, you can still purchase it. Only the operating cost will go up in this case. Your investment cost is not going up by purchasing steam. Okay. But this sorry, by purchasing oxygen, but for steam you'll require boilers and superheaters within your premises. You cannot purchase steam just like that, right? It's going to be very expensive. So you need boilers and superheaters. That will increase your investment costs, and then you'll need to produce the steam itself, for which you are consuming fuel, which is increasing your operating costs. Okay. So
Yes.
another two more differences. One is a producer gas is formed. Producer gas is rich in nitrogen. So the LHV is about 4 to 5 megajoule per kg. In this case, in the case of oxy-steam gasification, syngas is formed, which is rich in hydrogen. So it has a very high LHV, which is about 15 to 20 megajoule per kg. So air gasification, the producer gas can be used for power or heat generation only. Okay, because it has low grade energy basically. But when it comes to oxy-steam gasification, it can be used for other value-added chemicals like hydrogen, methanol, and other liquid fuels and chemicals. Okay, so these are the differences. So let me ask you this. So producer gas has about, I think, about 12% hydrogen, and syngas is about 50% hydrogen. So if I want to extract hydrogen from both, okay, I can do that. But why am I not doing it from producer gas? Why only syngas?
Because whatever plant we have, it is not efficient. It is not.
No, it's not about efficiency. I just told you the answer also. I mean, see, okay, there are two things to it. One is the
Because of
amount
the
of
larger
producer gas.
percentage.
Sorry?
Because of the larger percentage, is it?
That is one thing. The other thing is because of the presence of nitrogen in producer gas. Okay. The producer gas is nitrogen. It is incredibly hard to separate the hydrogen when there is a large amount of nitrogen present. Whereas in the case of syngas, there is no nitrogen present. You can easily separate it.
Yes.
Okay. So that is the reason. So some definitions, I'll tell you flame propagation rate. It's okay. The flame starts at the oxidation zone because that's where most of the oxygen is concentrated, and the flame moves slowly upwards into the other zone. Okay. So the rate at which the flame front moves up, okay, in the reactor, it's called the flame propagation rate. It's measured in millimeter per second. Okay. Then one very important definition is steam to biomass ratio. So if you're going for oxy-steam gasification, so there are two things. One is the equivalence ratio, which we already saw. Okay. So oxy-steam gasification, there are two things here: oxygen, there's steam. Okay. So oxygen is governed by the equivalence ratio. The steam is governed by the steam to biomass ratio. It is the amount of steam utilized for the biomass feed. That is, if you're using, let's say, 2 kgs of or let's say 10 kgs of steam for 5 kgs of biomass, then your SBR is 2. Okay, because you're for 1 kg of biomass, you're using 2 kgs of steam. So how many kgs of biomass have you used for how many kgs of how many kgs of steam have you used for how many kgs of biomass or per kg of biomass? So that is SBR. Then you have carbon boundary point, which is so you have char inside the reactor and you have the steam. Okay, the steam is reacting with the char. So if the steam content is more, then at one point what happens is that all the char is consumed by the steam, and there is more steam inside the reactor, right? So that steam cannot react with any more char. Okay. So and then what happens is the additional steam that is there, it starts reacting with the carbon monoxide that is formed. So that is water gas shift reaction. Okay. So it is the point at which all of the residual carbon is consumed. Okay. And the water gas reaction ceases to occur. So that is the carbon boundary point. So that can be seen over here. See, so this is steam to biomass ratio. As it is increasing, okay, theoretically you can say that, okay, I want my gas to be rich in hydrogen, so I'll just keep on increasing my steam content within the reactor. But that will never work, because as long as you have carbon, as long as you have char within the reactor, the steam will react with it. But at one point, the char will cease to exist because all the char is consumed. So that is this point. So the concentration, the hydrogen concentration increases, carbon conversion keeps on increasing until this point. And then after that, whatever steam you give is unreacted. So there is no conversion after this. Okay. Now, if you see the other one, the SPR versus H2 yield, of course, as you increase the steam to biomass ratio, the hydrogen is increasing. But this is only until this point. And as you increase the, this is equivalence ratio versus composition. As you increase the equivalence ratio, the hydrogen composition decreases. So the question here is, why is the hydrogen yield increasing with SBR but decreasing with ER?
Because in SBR, we are actually providing more steam to it, which is water. And in ER, we are considering oxygen. So more the oxygen, more water is formed. And
exactly.
When steam is given, it will produce more H2.
Yeah, yeah. So when more steam is given, the steam reacts with the carbon and the carbon monoxide inside to produce more hydrogen. But when you increase the oxygen content within the reactor, we are moving towards combustion, more towards combustion. So as if you remember from that diagram that we saw, the hydrogen content reduces as we increase the equivalence ratio. Okay, as we give more oxygen to the reactor, we move from H2 to H2O. Okay, and that is the reason why this happens. Okay, so that's it for today. Any doubts? We'll do some problems tomorrow based on this and based on the I was telling you about air as oxidizer, right? Instead of oxygen. So we'll do that tomorrow.